All right, with that, we will start. Thank you so much, Jennifer, that you're joining us. Just a quick introduction for the people in the room who don't know yet. Our next speaker is Jennifer Hu, who recently defended her PhD in brain and cognitive science at MIT, and will start as a research fellow at the Kemper Institute of the study of natural and artificial intelligence, actually this fall at Harvard University. Jennifer is interested in the computational and cognitive principle underlying human language to then understand better the human mind, but also build better AI systems. I'm very excited to see what you have prepared for us today, Jen, and the stage is yours.
Awesome. Thank you so much, and thanks for putting on this really cool event. So in our everyday lives, language feels really easy and natural, but it actually involves incredibly complex computations. So for example, imagine you're at your favorite coffee shop, the barista says, "Here's your latte," and you think to yourself, "I should take the drink and move away so that other customers can order." So there's a lot going on even in the simple interaction, right? You're receiving this continuous auditory signal or perceptual input, which you have to parse into discrete sound units and infer that those sounds correspond to a full linguistic utterance, like "here's your latte." And then you're not just interpreting this utterance at face value, you're integrating the meaning of these words with the physical and social environment that you're in to arrive at this final mental state and a plan for physical actions. So even in these really simple interactions, language involves incredibly complex computations. And yet, across societies and cultures, nearly every typically developing child will learn a native language with minimal explicit supervision. And within communities of language speakers, communication unfolds for the most part effortlessly and successfully, even in the presence of noise and ambiguity. So this kind of motivates my two main research questions that I'll talk about today. The first one is, what kinds of inductive biases could support language learning? And the second question is, how do we interpret language so flexibly and often go beyond what's literally said in a speaker's utterance? So these are two long-standing questions in language research, but in practice, they're often difficult to investigate with mathematical precision and natural scales. So from the learning perspective, one of the major challenges is that, of course, it's infeasible to manipulate language learning in humans, and there are few, if any, viable animal models for studying language with the full complexity of human languages. And then from the comprehension perspective, one challenge here is that although we have computational models and theories of language comprehension behaviors, oftentimes the precise predictions will depend on quantities that are often difficult to estimate in natural scales. This could include things like the priors or likelihoods of meanings, the costs of articulation or inference, and even common sense knowledge about the world. So these challenges have been facing our field for a long time, but in the current landscape of language research, we now have models, in particular neural language models, which are capable of really sophisticated linguistic behaviors. And importantly, not only do these systems show many of the signature complexities of human language, but we can also intervene in their learning and inference procedures. So for example, we can change the amount or type of training data that they receive. We can tweak the learning biases of the model, and we can also tweak the task that the model is optimizing for. And beyond learning, we can also intervene on inference mechanisms like different algorithms for decoding, but in this talk, I'm going to focus on the learning component. So in this sense, these models allow us to perform controlled manipulations in experiments that wouldn't be feasible to do in humans or other living organisms. So concretely, what can this tell us about the human mind? So at the end of the learning process, the language model will represent an optimized solution for the computational problem that's characterized by all these different variables. And this view of language is useful if we adopt the framework of rational analysis. So if we assume that cognitive systems like the human mind are adapted to their environments and goals, then by studying these external factors, we can characterize how these systems work from the inside. And in this sense, if language models in humans are solving similar computational problems, then we would expect them to display similar behaviors as solutions to these problems. And conversely, if we find that models show signatures of human-like linguistic generalizations and behaviors, then this could suggest that those behaviors in humans emerge as an optimal solution to this computational problem of statistical learning applied to linguistic forms. So concretely, in today's talk, I'll be illustrating this approach through kind of like this recipe through case studies. So the first step in this recipe is to identify behavioral signatures of human linguistic knowledge, and then design a way to evaluate or measure whether language models exhibit these signature patterns. And then finally, if we find positive results, then this suggests that the behavior of interest could, in principle, emerge through statistical learning and linguistic experience. And to be clear, these positive results wouldn't offer direct or mechanistic evidence that humans are learning in this way, but it adds plausibility to this argument or this idea. So I'll be demonstrating this general approach in 3 case studies, which use neural network language models to investigate these 2 big research questions I introduced earlier. So first, I'll talk about the role of inductive bias in learning syntactic generalizations. And then I'll shift gears and look at the comprehension side. And I'll talk about 2 projects about pragmatic inference. The first will be about inferences that arise from unspoken or unsaid alternatives. And then I'll talk about what language models can tell us about a broader class of non-literal language understanding phenomena. So now I'll go ahead and get started with the first project. And this is in collaboration with John Gauthier, Peng Chen, Ethan Wilcox, and Roger Levy. So I'm sure many of you are familiar with this already, but one central component of linguistic knowledge in English is hierarchical syntactic structure. And just to give a super quick example, I'm sure many of you have seen this. You could take a sentence like the keys to the cabinet are silver and illustrate the syntactic structure of the sentence with these kinds of relationships. And we notice that the noun keys needs to agree with the verb are in number. So since keys is plural, are must also be plural. But there's also this intervening content in the middle here, which is cabinet, a singular noun. So if the structure of English was such that the verb needs to agree with the linearly closest noun, then in this sentence, it would have to agree with cabinet, which is singular, but that's not the case. Instead, we have this dependency between keys and are, which are farther apart linearly. So this syntactic relationship needs to persist in a hierarchical way. Now, one of the long-standing debates in language research is how exactly these hierarchical generalizations about syntax are acquired, and more broadly, how do language learners generalize from the linguistic stimulus with which they're presented? And one kind of theoretical framework for this question is nativism, which argues that acquiring syntax requires innate and language-specific inductive biases. And a strong version of this hypothesis would say that a statistical learner that's exposed to finite positive examples of English sentences is not going to be able to converge on the correct hypothesis. An alternate theoretical framework is emergentism, which argues that linguistic knowledge could emerge through experience with linguistic forms over time. So this big question that we have is, can syntactic knowledge arise from domain general algorithms applied to linguistic forms, or do we need some more structure baked into the learning process? Now, ideally, we'd compare 2 types of child learners, but it's unclear how we can manipulate inductive biases in children and really focus on this problem of learning from linguistic input, right? So we need a different way to operationalize this idea of domain general algorithms applied to linguistic forms. And this is where neural language models can come in. So the general approach will be to compare the syntactic generalizations made by humans versus the syntactic generalizations made by language models. So to do this, we need a way to tell whether a model has learned the right syntactic generalization. And I'll just illustrate an example of how we would do this for the sentence that we saw earlier. So let's say we're interested in testing subject-verb agreement. We would create two versions of the sentence prefix, like the keys to the cabinet and the key to the cabinet. And importantly, they only differ in this one feature of the number feature of the subject. So keys is plural and key is singular. And then we feed each of these prefixes to the model, and then conditioned on each prefix, the model will give a probability distribution over potential next words. And in particular, here we can compare the probabilities of the plural verb are versus the singular verb is, conditioned on these two prefixes. And we expect that a model that's learned the correct generalization for subject-verb agreement should satisfy this pattern, where plural verbs should have higher probability conditioned on plural nouns, and singular verbs should have higher probability conditioned on singular nouns. And we can write this general prediction more precisely as this kind of conjunction of inequalities. And this gives us a success criterion. So if a model satisfies this criterion, then it suggests that the model has learned something important about the underlying syntactic phenomenon. And so that was just illustrating an example with subject-verb agreement, but to gain a more comprehensive look at syntactic generalization, we compiled these test suites covering a really large set of phenomena, which we divided into 6 groups shown here, which are based on the type of potential algorithmic strategy that's needed to successfully process each type of construction. And for each test suite, we designed a success criterion, or like an inequality, like from the previous slide. And then we compute an average syntactic generalization score as the average accuracy over all these items. And I should mention that these test items were manually written, and many of them were taken from syntax textbooks to ensure proper coverage and to make sure the items were semantically made sense. So going back to our underlying theoretical question, we're interested in what properties of a learner affect its ability to learn syntactic generalizations. And to get at this, we performed a series of controlled experiments where we trained a large set of neural language models manipulating inductive bias and training data set size. So first I'll talk a little bit about the different architectures that we tested. So as a baseline, we just had an n-gram model. And we also tested a vanilla sequence-based LSTM with no hierarchical bias. And then we had 2 models with some form of hierarchical bias. So the ordered neurons LSTM is similar to vanilla LSTM, but with a soft bias for hierarchical structures. And then we also had a recurrent neural network grammar, which is based on an RNN, but it receives structural supervision during training, and it's trained to model the joint probability of a sequence of words and its syntactic structure. So it has a stronger hierarchical bias. And finally, we also have a transformer language model, and we use the GPT-2 architecture as an example transformer. Turning to training data, we trained each of these model types on each of 4 data sets, which we constructed from a news corpus called BLIP. And these ranged in size from 1 million tokens, which is our extra small size, to 42 million tokens, which is the largest size. And it's estimated that 42 million tokens is around the size of linguistic input that might be available to a 4-year-old human. So these data sets are within a plausible range of data sizes for human learning, and they're much smaller than the data sets that modern language models are usually trained on. So we crossed each of these architectures with each of these training data sets, and this resulted in 20 different model types. And we had multiple random seeds for each model type. And we also compared these controlled models to 5 models that we just took off the shelf. So these models were not trained on these data sets, and they're also orders of magnitude larger in terms of the size of their training data and parameter count, but we included them just as a comparison. So first, let's look at the raw accuracy scores for all the model types. So the y-axis is going to be the syntactic generalization score, which is the accuracy ranging between 0 and 1 on all the test items that I mentioned earlier. And then the x-axis will show the different model types that we tested. So this includes our controlled models, which we trained specifically on our controlled data sets, as well as these off-the-shelf models, which are much larger, and the names are marked here with asterisks. So here are the accuracy results. The dashed horizontal line is the random chance baseline. And if we zoom into specific results here, first, we notice that the n-gram baseline doesn't perform above chance. So this validates that our experimental materials are being solved with local word statistics. And then if we focus on the best performing models, we see that the off-the-shelf GPT-2 models are achieving relatively high syntactic generalization scores, suggesting that they're capturing many aspects of English syntax. Now, another interesting finding is that the hierarchically supervised RNNG model achieves similar performance to much larger off-the-shelf models. And just as a reminder here, the RNNG performance here is shown averaged over multiple models that are trained on corpora, ranging in size from 1 to 42 million tokens. And for comparison, the JRNN model on the left here was trained on 800 million tokens. So this is a suggestive piece of evidence that model architecture can influence syntactic generalization abilities above and beyond sheer data size. And we can test this question more systematically by focusing on our controlled models, where we factorially manipulated architecture and training data size. So this allows us to draw direct comparisons. And so here on the y-axis, we're just showing the syntactic generalization score delta. So that's just the delta from the mean score achieved among all of our controlled models. And so if we separate or look at this performance separated by architecture versus training data, what we find is that architecture has a larger effect on syntactic generalization score than data size. So the models separate more cleanly by architecture than by the type of training set that they were trained on. And we also find that the purely sequence-based LSTM is underperforming the hierarchical models, the ordered neurons LSTM and the recurrent neural network grammar. So going back to our original question, can syntactic knowledge arise from domain general algorithms applied to linguistic forms? So in this project that we did, we showed that language models can enable us to perform a controlled evaluation of syntactic generalization that would be infeasible in humans. And we found, on the one hand, that large pre-trained models achieve high syntactic generalization scores, suggesting that domain general algorithms can learn syntax from just linguistic input. But we also found, on the other hand, that model architecture has a larger effect than training data size. And in particular, we found that a hierarchical inductive bias helps with learning syntax in these smaller settings. So overall, these results provide evidence against strong nativist claims about the necessity of inductive biases for learning language, but it also highlights that inductive biases can be important for language learning in small data settings. So we just talked about inductive biases for learning language, and now I'm going to talk about two projects related to how we interpret language pragmatically and flexibly in context. So the second project will be about inferences about the unsaid, and this is joint work with Roger Levy, Judith Dagan, and Sebastian Schuster. So as many of you probably know, humans interpret language in very flexible ways, and we often go beyond just literally interpreting what speakers say. And one important example is that what people choose not to say is often just as informative as what people do choose to say, as you can tell in this scene from the TV show 30 Rock. In this project, I'll be focusing on scalar implicature, which is a canonical example of this kind of pragmatic reasoning about unspoken alternatives. So just to make sure we're all on the same page here, let's say your friend says the utterance, "When I got home, my dog had eaten some of the cookies." So what do they mean by this? Well, clearly they're conveying something about the number of cookies eaten. And in a strictly logical sense, saying that the dog ate some of the cookies will be compatible with the dog eating any number of cookies greater than 1. And saying that the dog ate all the cookies is compatible with only this endpoint, like n out of n cookies were eaten. And so we're going to call this ordered relationship a scale, where a weaker or less informative scalemate like some overlaps in meaning with a more informative scalemate like all. And in addition to the scale some and all, scales can be formed by other lexical items and parts of speech like warm and hot, or possible and certain, and so on. So returning to the example, there's this overlap in meaning between some of the cookies and all the cookies. And so in this logical sense, some has a meaning that's similar to some and possibly all. But in a naturalistic communication, a human listener might reason that speakers are generally cooperative and they want to be informative. So if the speaker knew that the dog had eaten all the cookies, then they would have just used the word all instead of some. So on the basis of this unspoken alternative sentence with all, the listener can rule out the meaning of all and arrive at an interpretation of some that's closer to some but not all. Now, as we just saw, these scalar inferences are driven by the set of unspoken or alternative utterances. And in principle, every possible utterance in a language might be an alternative to every other utterance. But this is problematic for several reasons. So first, at an algorithmic level, it'll be intractable for listeners to perform inference over the entire set. And maybe more concerningly, scalar inferences wouldn't arise without additional restrictions on the alternatives. So the expected pattern is that the weak scale mate some combined with negating the alternative all will lead us to scalar inference some but not all. But without a way to restrict the alternatives, the expression some combined with some but not all would lead to the inference all, right? And this gives us a contradiction. So it's a theoretical puzzle of how the set of alternatives is restricted. And this brings us to the next kind of big question for this project, which is how do listeners determine the unspoken alternatives considered by the speaker? And ideally, we'd like to be able to probe humans' expectations about the things the speaker could have said. But this is a kind of unnatural task and hard to probe through top-down introspection. And it's also expensive to get large-scale estimates this way for arbitrary contexts. So what we're going to do is we're going to use neural network language models to stand in as approximations for human predictive distributions. And in particular, we're going to be testing an expectation-based theory of alternatives. So the idea is that since alternatives are unspoken by definition, listeners must maintain some uncertainty over them. And they're using contextual and grammatical cues to maintain probabilistic expectations over likely alternatives. And the intuition here is that if a scalemate is more likely to be considered by the speaker, then the speaker's choice not to use it should provide greater evidence that it's not true or that didn't have grounds to say it. And so we expect a stronger a tendency to negate that unspoken alternative, and the scalar inference should be stronger. So this makes the following general prediction. The more expected the strong scalemate is as an alternative to the weak scalemate, the higher scalar inference rates should be. So this theory has mostly been tested qualitatively in small settings. And to operationalize this theory at a larger scale, we're going to use neural language models to estimate human expectations over which alternatives are likely to be strong scalemates. So the empirical phenomenon that we want to explain here is variation in scalar implicature rates, right? And these inferences vary in two senses. First, they vary across contexts within a single scale, like some and all. And second, they also vary across scales formed by different lexical items. So let's walk through some examples in the next few slides to give you a feel for the data. So first, let's look at variation within the scale some and all. I'll show you some pairs of sentences, one with some but not all, and one with just some, and then I'll ask you to rate how similar those two sentences are in meaning on a scale of 1 to 7. So 7 is the highest, and a score of 7 would mean the sentences basically mean the same thing. So here's one example. I like some country music, and I like some but not all country music. So think in your head of a number between 1 and 7, how similar these sentences are in meaning. So in this empirical study conducted by Judith Dagan, she found that across a large number of people, the average similarity rating here was 6.9, very close to 7. So these sentences basically have the same meaning. And then if we consider a different pair of sentences, like it would certainly help them to appreciate some of the things that we have here. And it would certainly help them to appreciate some, but not all of the things that we have here. Now, yeah, again, think of a number between 1 and 7 in your head. So in this same study, Judith found that people only rated the similarity here at 4, which is in the middle of this rating scale. And these two examples are taken from this broader study of over 1,000 pairs of sentences with some and all. These are all naturalistic sentences from a spoken corpus. And this plot just shows the distribution of similarity ratings ranging from 1 to 7. And we see there's a lot of variation in the ratings. They aren't all just concentrated at the high end of the scale, right? So this suggests that inferences across contexts within a single scale, like some and all, can be quite variable. And now, as I mentioned earlier, scales can also be formed by different lexical items, and scalar inference rates vary across these scales. So let's do some more examples. John says success is possible. Would you conclude that John believes success is not certain? Think in your head of whether you would say yes or no. And in this empirical study, Van Thiel and colleagues found that there's like a 93% rate of people responding yes to this question, suggesting a strong or high scalar implicature rate. But then if we look at a different scale, John says the painting is ugly. Would you conclude that John believes the painting is not hideous? Only 18% of people said yes. And again, these two examples come from this broader empirical study. And this shows the mean scalar implicature rates across many different scales. And so each bar here is a unique scale. And again, we see a lot of variation ranging from 4% all the way up to the high 90s. So we've seen how scalar inference rates can vary, both within a single scale like some and all, as well as across scales. And now let's talk about how we're going to use language models to estimate the expectedness of alternatives. So intuitively, the listener's task in scalar inference is, given the context and the weak scalemate, how likely are the weak scalemate and strong scalemate to be in a scalar relationship? If this is more likely, then the meaning of the strong scalemate should be more likely to be ruled out. But it's unclear how this quantity should be estimated. So our approach is to reframe this as the problem of estimating how likely the strong scalemate is to appear in a scalar construction with a weak scalemate. And so I'll give an example of this on the next slide, but scalar constructions are essentially sentence templates that suggest a scalar relationship between items. And with this approach, we've turned this relevant quantity into something that we can directly measure with neural language models. So concretely, we use a scalar construction X, but not Y. So for example, if humans see a sentence like the food was fine, we create a version of that sentence that says the food was fine, but not blank. And this construction suggests that whatever goes in the blank is a strong scalemate to the weak scalemate, fine. And the idea is that humans are going to maintain some expectations over what word could go in the blank, for example, great or delicious. And we can use language models to approximate this human predictive distribution. And then if we look at this probability distribution under the model conditioned on the scalar construction, then we can measure the expectedness of any given scalemate, for example, delicious. So for any given scale formed by a weak scalemate and a strong scalemate, we take the negative log probability or surprisal of the strong scalemate conditioned on the scalar construction context. So a lower surprisal here corresponds to higher probability or higher expectations. And so the expectation-based theory of alternatives will predict a negative relationship between the surprisal of the strong scalemate and human scalar implicature rates. So a final note on this is that implementing this idea at this level of specificity raises an interesting problem. So in particular, the surprisal measure treats alternatives as strings, which reflects the assumption that human listeners are reasoning about unspoken alternatives at the level of linguistic forms. But this might not be the right level representation for alternatives. So for example, let's say we have a scalar construction like the problem is hard, but not. We can compute the model probability assigned to a large set of candidate alternatives. And for this particular item, the empirically tested strong scalemate is the word unsolvable. It could be the case that the model assigns low probability to the word unsolvable, but high probability to words like impossible and unreasonable, which essentially convey the same information as the actual tested strong scalemate. So to illustrate this more visually, you can imagine that there's a space where there's a continuous conceptual similarity measure where alternatives like impossible and unreasonable are very close to unsolvable, but a word like sheepish would be very far away. And in this sense, we can think of this cluster of string alternatives as reflecting a single underlying conceptual alternative, which we can describe as something like very hard. And it could be the case that we want to estimate is the surprisal of this conceptual cluster, but what we have tangible access to is string probabilities under a language model. So we have two different implementations of this expectation-based theory. For the string-based implementation, we just use the surprisal estimation that I described earlier. And for the concept-based implementation, we compute a weighted average surprisal, which is a sort of smooth measure that takes the conceptual similarity into account. So ignoring the math for a moment, the intuition is that each candidate alternative string will contribute its raw probability, but this probability is weighted by the similarity to the tested strong scale mate. A few quick notes on the implementation details. We get the set of alternatives from a large set of items from English lexical database. So essentially, this is just a large list of adjectives or adverbs or verbs, depending on the part of speech of the scale. And to operationalize similarity, we use cosine similarity between the glove embeddings for the candidates. Okay, so now finally we can turn to the results. And recall that we have two empirical phenomena we want to explain. We have variation across contexts within the scale, some and all. We also have variation across scales. And we're going to be testing implementations of the expectation-based theory that reflect different representations of alternatives. So we have string-based and concept-based. And as a reminder, we're testing for this general pattern, a negative relationship between human scalar implicature rates and the surprisal of a strong scale mate. So first, let's look at within scale variation. And let's start by looking at a string-based surprisal measure. So each dot here is a single sentence context, and we find the predicted negative relationship between the human scale implicature strength ratings and the surprisal of the strong alternative all. And we also find the predicted negative relationship for the weighted surprisal measure. And in fact, it's even a little bit stronger here than for the raw surprisal measure. Now, visually, it kind of appears that the dots are very highly concentrated in the low regions, and the relationship doesn't look very linear. But it actually turns out that the surprisal of all is so low in most cases because sum and all is such a strongly lexicalized scale. And so a lot of the values are concentrated around 0. But if we actually look at this in the space of raw probabilities and not surprisals, the relationship looks a lot more linear. And regardless, the relationship is negative. Okay, so we found the predicted relationship for both cases for within scale variation. And now we can turn to variation across scales. And here we're testing our predictors on 4 empirical data sets of human scalar implicature rates. And there's around 150 unique scales in total across these data sets. And again, let's start by looking at the string-based surprisal of alternatives. In this case, we only find a significant negative relationship for one of the 4 tested data sets. But then if we turn to the concept-based treatment of alternatives, or the weighted average surprisal, then we find the predicted negative relationship for 3 out of the 4 data sets. So for cross-scale variation, we only find that expectedness as a robust predictor under a concept-based view of alternatives. Okay, so to summarize, going back to original question, how do listeners determine the alternatives considered by the speaker? In this work, we use language models to test expectation-based theories of alternatives in a large-scale systematic way. Our empirical test data was variation in scalar inference rates, both within the scale sum and all, and across scales formed by different lexical items. We found that both types of variation are captured by expectations over alternatives, but with the caveat that these expectations seem to potentially operate at the level of concepts instead of raw strings. And more broadly, these results suggest that scalar inferences might arise based on context-driven expectations about what was unsaid. And this highlights how experience with linguistic forms can be leveraged to make predictions that are used in pragmatic inferences. Okay, so in the second project, we just did a deep dive into scalar inferences, which is one example of how humans interpret language beyond what's literally spoken. And in the final project, I'll then turn to a broader range of non-literal language understanding phenomena. And this is joint work with Sammy Floyd, Alessia Dravlev, Ev Fedorenko, and Ted Gibson. So non-literal language is everywhere in natural conversation, going far beyond the scalar implicature examples that we looked at. So just to give some really quick examples, if your friend is sitting next to an open window and they say, it's cold in here, they aren't just making a statement about the temperature in the room. You might infer that they're trying to ask you to close the window indirectly. Other examples include ironic statements where the meaning of what a speaker says is the exact opposite of what they are literally saying, or polite deceits and white lies, where a speaker uses a particular utterance to mean something that conflicts with their true feelings or mental states. So what kind of mechanisms could support such flexible non-literal inferences? So at the courses level, there needs to be literal language understanding that's grounded in knowledge about the world, right? So for example, in interpreting an indirect speech act like it's cold in here, the listener needs to know what cold means and that it's an unpleasant physical state. And these inferences are also highly dependent on cultural and social norms. So for example, it might be inappropriate to use a direct request, like forcefully commanding close the window. And this information might all be integrated through mental reasoning processes where listeners are considering the speaker's intentions and mental states. And this has been formalized in iterated reasoning models like the Rational Speech Act framework, which is illustrated here in a cartoon form. Essentially, the idea is that a listener interprets a speaker's utterance by reasoning about a speaker who is in turn designing their utterance by reasoning about a listener. And this kind of back and forth reasoning could, in principle, continue for an arbitrary number of iterations. So there's a lot of evidence supporting these kinds of models and the role of mentalizing in small-scale experiments. But in practice, arbitrary levels of reasoning about other people's minds could be very slow and cognitively effortful. So a hypothesis to explore is that non-literal language understanding might reflect less sophisticated reasoning mechanisms and could instead arise through sufficient experience or features of linguistic signal. So the big question I'll investigate in this case study is what kind of aspects of non-literal language understanding could arise without explicit symbolic theory of mind? And again, ideally, we would compare two versions of humans to kind of get at this question, but we can't do that. So as you probably have expected by now, we're going to use language models instead. So our stimuli for this consists of a set of manually curated test items, and these each take the form of a multiple choice question, which presents a story and then asks for interpretation or explanation of the character's utterance. So here's a quick example. Nate is about to leave the house. His wife points at a full bag of garbage and asks, "Are you going out?" What might she be trying to convey? So for this particular item, there were 4 possible answers. She wants Nate to take the garbage out. She wants to know Nate's plans. She wants Nate to spend more time with the family. And she wants Nate to bring his friends over. And these 4 answer options, in this case, correspond to 4 different strategies for answering the task. So option 1 is considered the correct non-literal interpretation of the utterance. Option 2 is a literal interpretation. For example, like Nate's wife is asking if he's going out because she's genuinely curious about his plans. So this option is not semantically wrong, it's just implausible. And then the 3rd and 4th options are distractor options, which still reflect non-literal interpretations of the utterance, but they aren't very plausible. And they're constructed to be related to the context and the utterance through low-level heuristics. For example, answer option 3 has high similarity in lexical items like family, house, and garbage. And option 4 has semantic associations, like the idea of going out and bringing friends over. So that gives you a sense of what these items look like. And the stimuli were designed to cover a broad range of phenomena that reflect different ways in which language can be used non-literally. So for example, for polite deceits or irony, speakers conveying the opposite of what's literally said. Other phenomena like metaphor might require figurative language. Indirect speech acts and Gracian maxims might require inferences based on social conventions. And we also tested humor, which seems to reflect a completely different kind of language reasoning and understanding. And a final note is that these items were designed to elicit differences among humans. So there's going to be fine-grained variation, which will allow us to do a comparison between models and humans at the item level. For our evaluation paradigm, we had multiple choice questions through zero-shot prompting. So we chose to use prompting because all the inputs are in natural language and there's no task-specific formatting. So this will allow us to compare performance across tasks within models. And we use zero-shot prompting because by not having any examples for the model to learn on in the prompt, we can test the knowledge that emerges just through the training process and not through on-the-fly task adaptation. So I'll show you an example prompt really quickly. So recall the example item that we walked through earlier. Here's what that exact example looks like in prompt format. So first we have a set of task instructions. That's just like you will read short stories that describe everyday situations, answer with 1, 2, 3, or 4. And then we have the scenario, question, and answer options, which we walked through earlier. And this is all nearly identical to what humans saw in the behavioral experiments. And then the way that we evaluate models is based on the prediction of the next token condition on this entire prompt. So we're just comparing the probability of the tokens 1, 2, 3, and 4, which correspond to these answer options. We tested several model families of different sizes. So we have GPT-2 as a baseline, and this model was just trained on autoregressive language modeling. So it might not perform very well on the prompting-based task. And then we tested 2 classes of models that are both fine-tuned on a variety of tasks. And within each family, we tested 2 sizes of models, one small and one large. So we have 2 TK instruct models and 2 Flan T5 models. We also tested 2 models based on the instruct GPT-3 architecture. And these are also fine-tuned on a variety of tasks, and there's some human alignment. Then finally, we have a random baseline and a human baseline. And the human baseline was empirically measured from 374 humans from a concurrent study. Now, I want to point out, before getting to the results, that unlike in the first 2 projects, here we're testing models with instruction fine-tuning on top of the standard word prediction pre-training objective. And this has several practical implications. So first, it enables us to use zero-shot prompting as our evaluation paradigm. And this is advantageous for some of the reasons that I alluded to earlier. Right? And also, these models have a better chance at capturing some of these prerequisites for these kinds of pragmatic inferences, like world knowledge and social common sense. And on the other hand, this choice to use these instruction fine-tuned models also has theoretical implications. So unlike in the first 2 projects, the model outcomes are no longer going to tell us about the task of word prediction and whether this is the exact computational objective that humans are trying to solve. Instead, in this particular instance, what we're interested in and what these models can potentially tell us is about data structures and representations. So these models don't have any structured symbolic reasoning representations of other agents. And so if they're capturing human-like pragmatic inference behaviors, this suggests that these inferences could arise through language statistics and implicit connectionist models of agents and world states. Okay, so with all that out of the way, now let's look at the results. First, I'll just show task accuracy. So the y-axis is the proportion of items where models or humans selected the pragmatic correct answer. And then the x-axis corresponds to the different phenomena we tested in our stimuli. So here are the results. If we first just focus on the brown bars for a moment, we see that humans generally do very well across all the tasks. And then they're closely followed by Text Da Vinci, which is the dark blue bars. And then these are also followed by the other larger models, which are Flan T5XL and TK Instruct 11 billion. So there's certainly room for improvement, and the models aren't doing perfectly by any means, especially on tasks like humor and Gricean maxims. But we do find that the largest models are performing consistently above chance, and in the case of Text Da Vinci, in some cases near human level. So it's suggestive that the models are capable of selecting pragmatic responses in many cases. Now, going beyond just accuracy scores, we can also analyze the full shape of the distribution of responses. And this will allow us to analyze whether models and humans are making similar error patterns above and beyond how often they choose the correct answer. So first, I'll illustrate this for one of the tested phenomena, deceits, and then I'll zoom out and show you the results for the rest of the phenomena. So the x-axis here corresponds to the different answer options. So we have the correct pragmatic answer, the literal answer, and then some distractors based on simple heuristics. And the y-axis is going to correspond to the probability assigned by the model to each answer option. And for humans, the frequency that humans selected that answer option. And the horizontal dashed line is just a random chance baseline. So I'll walk through the results, starting with humans. Here are the human response frequencies. Clearly, they select the correct pragmatic answer most of the time. And then their next preferred option is the literal answer, which is selected around 16% of the time. And then they rarely ever select the distractors. So we see this general kind of shape with the peak on the correct answer, a non-trivial probability on the literal answer, and then very small probability on the distractors. Now, it's not immediately obvious what to expect from models. They could potentially have a distribution that looks like this, or they could guess more uniformly among the incorrect literal and distractor answers, or they could be really distracted by the distractors and reliably choose those options over the literal option. So for the text Da Vinci model, we see a very similar pattern to humans, where the model prefers the literal option over the distractors. And again, we see a similar qualitative pattern for the other two large models, the TK Instruct 11 billion and Flan T5XL. And their quantitative fit isn't quite as good to the humans distribution because they make more errors in general, but again, we see this general curve. And then for the rest of the models, we see they perform pretty poorly, and many of them have a pretty uniform distribution. Although interestingly, the smaller TK Instruct and Flan T5 base models are actually selecting the literal option the most often out of all the options. So this was just for one of the tested phenomena. And now we can zoom out and look at the response distributions over all the phenomena that we tested. Now, there are a lot of bars here, but the main takeaway is that, again, we find a similar pattern across the phenomena demonstrated by these curves that illustrate the pattern of human responses. So for the large models, when they're not correct, they consistently prefer the literal interpretation over the heuristic-based distractors. So we find that models are mirroring human response distributions, where they prefer the pragmatic correct answer over the literal answer, and then they rarely get distracted by the heuristics. And this suggests that when the models are not selecting the correct pragmatic answer, it's not because they're not getting some kind of literal meaning, it's because there's some gap between going from that literal meaning to the non-literal pragmatic interpretation that humans are preferring. I have a few more results on this, but in the interest of time, I think I'm going to skip to the kind of summary for this project and conclude. So returning to the original question for this project, what aspects of non-literal language understanding can arise without explicit theory of mind? We found that language models are producing human-like response distributions for many different non-literal language understanding tasks. And through behavioral experiments and analyses, we found that models and humans might be leveraging linguistic cues in similar ways. This is the results that I skipped, and I'm happy to talk about them more if people have questions. And more broadly, this suggests that pragmatic behaviors could be captured without explicit representations of mental states, suggesting that in certain cases, structured reasoning mechanisms might not be necessary for non-literal language understanding. So in this talk, I've walked through 3 case studies using neural language models to offer insights into questions about language learning and comprehension. And now I'll conclude with a few final takeaways. So hopefully I've illustrated today that viewing language models through the lens of task optimization can provide a new way for cognitive scientists to perform controlled experiments to study language that would be infeasible to do in humans or any other living organisms. And through the 3 case studies that I talked about, we saw that language models capture many human linguistic behaviors, ranging from syntactic generalizations to fine-grained pragmatic inference patterns. And importantly, this doesn't provide direct evidence that humans are learning or comprehending language in any particular way, but it increases the plausibility of the idea that human-like language abilities could emerge through statistical learning and linguistic experience. And then zooming out for a bit, I think this suggests that these models are not just useful engineering tools, but if we control the way that they're trained and the way that they learn, they could actually serve as implemented theories of language processing. And there are a lot of exciting directions to explore in this space in the future. So I'll just wrap up there and say thank you to my collaborators and funding, and I'm happy to take any questions.